Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosine River College in Sacramento, California. This video is dedicated to a rare but kind of important theorem, the power reduction formulas and their use. So prior to this, it is very important that you have already worked with and understand the double angle identities for trigonometry. And that's these guys right here. So it's very important that you understand these identities. Remember, you do not have to memorize the tangent of the double angle, at least if you're one of my students. Your instructor might require you to memorize them, but I do not have you memorize the tangent of the double angle. The sine and the cosine, definitely, but not the tangent. And those formulas are required so that you can understand the power reduction formulas. So the power reduction formulas take something like a sine squared or a cosine squared and trade them out for cosines of lower powers. So you're taking even powers of sine and cosine and trading them out for lower powers of cosine. In fact, that's kind of the punchline here. So let me write that down. So there, I've written it in. These are used to take even powers of the sine and the cosine and rewrite them as lower powers of cosine of double angles. So let's go ahead and see the proof. The use of this, I have to be very honest with you. When I was in trigonometry, I don't ever recall actually seeing these. You see them in a different form called the half angle identities. But to be honest with you, we don't really use these that often. Now, your instructor might love them and say, well, if you heard that online, that person's a liar. But I teach all levels of mathematics, all the way through up to the upper division level. And let me just tell you, you don't really use these that often. But they are referenced quite a bit. You do hear of them in Calc 2 every once in a while, power reduction, power reduction. And so it is important that you at least have seen them. So let's take a moment. It only takes literally a moment to get to know these. So let's go ahead and just recall one simple but important formula, that the cosine of the double angle has, well, three representations, but I'm only going to really refer to two of them. The first one I'll refer to is 2 cosine squared of theta minus 1. Now, if I wanted to, I could add 1 to both sides. If I did that, I'd get to here, and then I could divide both sides by 2. If I did that, I get to there, and guess what we have? We have the second version of the power reduction formula. Like I said, it only takes a moment to talk about these. So you really all you're doing is playing with the double angle identity for the cosine and solving it for cosine squared. Same thing if you wrote the cosine double angle formula in terms of the sine. So it'd be 1 minus 2 sine squared. You could technically add 2 sine squared to both sides and subtract cosine of the double angle from both sides, and then divide both sides by 2. And if you do that, you'll get the very first of the power reduction identities, which is this one up above. So both of them are very fast to prove. Also, like I said a moment ago, these are most often known as the half angle identities, which is a different series of videos that I'll talk about in a little bit, in a different video, I mean. And so that's why I don't really pressure my students to memorize these, because you'll see them in a different form that's more useful in a future video. But let's just see these in action. Probably the most useful version of the power reduction formula is something like this. When you're asked to graph this by hand, graph y equals 4 times the cosine squared of x minus 2 by hand. So not using Desmos or calculator or anything like that, but by hand. Well, the cosine being squared is an issue. I know how to graph a cosine. I know how to graph a sine, but how to graph a cosine squared, nobody taught me. I'm saying that as if I'm a student, okay? So I need to be able to reduce this power, and the way I'm going to do it is just think of all the formulas that involve the cosine squared. For example, we know that sine squared of x plus cosine squared of x is equal to 1. Well, that's one formula involving the cosine squared. Unfortunately, if I were to say, well, let's trade that cosine squared out, let's solve for cosine squared. Okay, well, we could trade it out for 1 minus sine squared. That leaves me in the same predicament. I would be graphing a sine squared at that point, and I don't know how to graph a sine squared either. So this set of formulas is not going to help me. So I'm just going to cross them out. While they are true formulas or true identities, they're just not going to help in this situation. So then I think, well, what other formulas do I know that involve a cosine squared? Oh, I know one that involves a cosine squared. The cosine of the double angle. That has a cosine squared in it. I could write as cosine squared minus sine squared, but that is not really going to help me, because if I solve that for cosine squared, I'll be graphing a cosine of 2 theta plus sine squared, which is worse. But I happen to know that the cosine of double angle is actually twice the cosine squared of the angle minus 1. And so if I add 1 to both sides, cosine of 2 theta plus 1, and divide both sides by 2, I see, oh yeah, that's right. I can take a cosine squared and trade it out for a lower power version of cosine. That's the one I'm going to use. Notice I just reproved the previous theorem. Often that's what I was saying 1 or 2 videos ago when I said some of these you do not want to just skip over the proofs, because the proofs are important. You want to rederive things quite often in mathematics, mainly because it's good practice. Also, you'll forget formulas. And so being able to quickly rederive things, very, very powerful. So let's see. I can rewrite this cosine squared as a cosine of the double angle plus 1 over 2. I mean, just double check. Yep, that's exactly what it is. Now notice this 2 will go into this 4 nicely. And so I am then being asked really to graph y is equal to 2 times the cosine of 2x plus 1 and then minus 2. And you might say, well, I still don't know how to graph that. Well, it's only because you're not finishing out your arithmetic. Distribute that 2 and then clean things up. So this means we're being asked to graph y equals 2 times the cosine of 2x plus 2 minus 2. So this is actually what we're being asked to graph, and I could totally graph that. Remember, this is a graph of the form a cos of bx plus c plus d. If you do not know how to graph trig functions, please review my videos on graphing trigonometric functions. I have a whole series of them, and you'll understand what I'm doing if you watch those videos. But I'm not going to review that here. I'm just going to quickly do all the mechanics that I would normally have derived in those videos. So I know the amplitude for this graph is going to be 2. I know the period for my graph is going to be 2 pi over b, which is 2 pi over 2 in this case, or pi. I know the step size is the period over 4. And I like doing this, by the way, of constantly reviewing older skills so that students get, practice as they head to exams and stuff like that. Step size is period, which is pi over 4, so pi over 4. Our phase shift would be equal to a negative c over b, but there is no c in this case, so it's 0. And our vertical shift would be d, but there is no d, so it's 0 as well. Our midline, now we're going to start graphing. Let me get my ruler. Our midline will occur at the vertical shift, which is 0, so it's just the x-axis. I'll just draw the midline in. And that'll be the x-axis. We know we're dealing with the positive cosine. So I'm going to go ahead and plot the phase shift first. I kind of go backwards, so I've just drawn the vertical shift. I'm now going to plot the phase shift, 0. And now I'm going to go by step sizes. And remember, there are going to be 4 steps overall, but I'm going to just put in 4 little slashes here. And each of those are going to be by the step size of pi over 4. So this is pi over 4. Here's 2 pi over 4. Here's 3 pi over 4. And finally, 4 pi over 4. And as I mentioned in my videos on graphing, I don't have my students reduce those. Period has been taken care of because that's already taken into account when you do your step size. And now I'm going to draw in my y-axis, which occurs at x equals 0. And I can turn off my ruler. I don't need that. There's my y-axis. And now I'll go ahead and graph my cosine curve. It starts high, goes through, goes low, goes through, goes high. And so I'll connect those dots with a nice smooth curve. All done by hand, right? There we go. That's one period of this. We were being asked to graph this from 0 to 2 pi, but I'm just getting the 1 pi done first. Amplitude of 2, so that's 2, and this depth here, or the minimum, is a -2, because it's plus or minus 2 from the midline. And then they want us to graph until 2 pi, which I didn't really give myself a ton of room for, so I'll just extend this out. And I'll just do this. Boom, 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 and boom. 2 pi. Usually just labeling for a single cycle is fine, and then extending out like this is perfectly okay. So there you go. There is the graph of y equals 4 cosine squared of x minus 2. Something that you normally would not be able to do without the knowledge of the power reduction formulas, or at least the double angle identities. Normally I reserve proofs for my proofs and trigonometric identities videos, but power reduction formulas are rare enough that I don't want to burn a video just for that. So let's go ahead and just do a proof that involves a power reduction formula here. So we want to prove that 3 sine of theta minus 4 sine cubed of theta is equal to sine of 3 theta. Now, to be very honest with you, this is a tough proof, just because if I gave this on an exam or something like that, a lot of people would stare at this. They would not know how to even begin. It is not the easiest. There's a couple ways you can go about this. I could at least see 3 tactics right now. I'm going to start on the left-hand side. I could start on the right-hand side, but unfortunately the right-hand side is not a double angle, because that's not sine of 2 theta or 4 theta or 6 or, an even number times theta. So it's not a double angle identity. So that's going to be kind of a pain. I can force it, sort of, to be a double angle identity eventually, and we'll showcase that. But for right now, this is not an obvious identity. So instead of tackling the right-hand side, I will tackle the left-hand side. Now, tackling the left-hand side, I can easily see what some people might do here. Let me zoom in so that I don't have my pen go all jagged. The left-hand side is 3 sine of theta. I have to zoom out again just to see what I have. Minus 4 sine cubed. So minus 4 sine cubed. What a lot of students will do, and myself included, by the way, I'm totally going to do this. I'm going to factor out a sine out of both those terms. Why not, right? I'm left with 3 minus 4 sine squared of theta. That was supposed to be a squared of theta, but it just didn't quite work that way. Now, when you look at that, that does not seem to get anywhere near sine of 3 theta. I'd like to reduce that power if I can. I don't want a sine squared when I'm finished. I want a sine of 3 theta. So do I have a way of writing the sine squared? And the answer is yes. That sine squared right there is the same thing as 1 minus the cosine of 2 theta over 2. So I'm going to go ahead and trade out the sine squared of theta for a 1 minus the cosine of 2 theta over 2. That's the power reduction identity. And again, when we go into a future video, we'll deal with what's called the half angle identities, which is probably a more natural way of thinking about this. So don't get freaked out too much when you see this. All right, so let's go ahead and trade out my sine squared for that. So let's see, this is going to be a sine of theta. And then we have times the quantity 3 minus 4 times a 1 minus cosine of 2 theta. And this is all over 2. And you look at this and you say, it doesn't look anything like sine of 3 theta. Well, the problem is we don't know how to work with sine of 3 theta. So we're kind of locked on that side. So for right now, let's just continue forward. This is going to be the sine of theta times the quantity 3 minus 2 goes into 4 twice. And we still have a 1 minus, let's see, cosine of 2 theta. And let's go ahead and do our arithmetic here. Sine of theta times 3 minus 2 is 1. A negative 2 times a negative cosine is a plus 2 cosine of 2 theta. Okay. We get down to this point right here, and it looks like we're completely locked. Like we don't know what to do from this point forward. There's no trig identity that says, oh, 1 plus 2 times a cosine turns into something, so that's locked. We know that we could technically trade out a cosine of a double angle for its double angle formula, but then that would introduce cosine squareds or cosine squareds and sine squareds or sine squareds. And that's not where we want to arrive on the right hand side. So let's go ahead and press pause here, because I'm a little concerned that maybe we can't get to an answer this way. So I'm going to write in pause, and we're going to move to the right hand side. Now the right hand side looks like there's not much we can do, but I'm going to show you a little trick. The right hand side is sine of 3 theta. That's not a double angle identity, but you could write that as sine of 2 theta plus theta. Isn't that 3 theta? And if you do that, you now can use your sum of angles identity, which is a prerequisite for this material right now. So using our sum of angles identity, this would be the sine of the first angle times the cosine of the second angle plus, because sine keeps its sign, sine of the second angle cosine of the first angle. Okay, let's take a look at our green handiwork. You can see the green handiwork is not exactly that. It's close, but no cigar, right? So how are we going to do this? Well, I could either pause on the right-hand side and go back to the green, to the left-hand side to continue, or I could try a little bit more work on the right-hand side. And I like the idea of trying a little bit more work on the right-hand side because there's something that might just work out here. In fact, maybe what I'll do is I'll go over the green just to showcase my mindset here. Let's go over to the green and unpause. So I'm going to erase the pause and unpause for a moment. And I'm going to say, you know what? The red side, the right-hand side, didn't have this parenthesis here. So I'm going to distribute this. I'm going to say this is the sine of theta times 1 plus 2 times the sine of theta times the cosine of 2 theta. Now I'm going to hit pause again. Now I'm going to look over at my right-hand side. Notice on the right-hand side, I have something similar. I don't know if you could see it. I'm going to use a highlighter to showcase this. On the right-hand side, I have a sine of theta times a cosine of 2 theta. On the left-hand side, I have a sine of theta times a cosine of 2 theta. Well, I actually have two of them. So I'm going to have to do a little bit of a manipulation here, but I'm very, very close. Super close, actually. And in fact, what I think I'm going to do is I'm going to unpause on that, on the left-hand side one last time. Let me write pause on the right-hand side because I'm paused this work. I'm going to unpause on the left-hand side. And what I'm going to do is I'm going to keep on the left-hand side, I'm going to keep one of these signs of theta, cosine of 2 thetas. I'm going to split that up, actually, is what I mean to say. So I have a sine of theta plus sine of theta, cosine of 2 theta, plus a sine of theta, cosine of 2 theta. Now you might be wondering, why the heck is he doing that? I hit pause here. The reason why I'm doing that is because now you should see this matches that. So really now my work is just to make the other terms, let me highlight them, this guy and this guy, I just need those two to match now. The yellow highlighted stuff now matches. I need to get the blue stuff to match. So let's take a look at our options. I need sine plus sine of cosine of 2 theta to turn into sine of 2 theta, cosine of theta, or vice versa. And it doesn't really matter to me which side you want to work with, the right or the left. It actually does not matter. So I'm going to listen to you right now. Which side do you want to work with? Oh, you say the right-hand side? Great. I'll work with the right-hand side. So going to the right-hand side here, let me erase my highlight and unpause on the right-hand side. I'm going to trade out that sine of the double angle for 2 sine of the angle times cosine of the angle. And of course, that would be cosine times a cosine, so it'd be cosine squared. And remember, this stuff at the back end is locked. I don't want to touch that because it already matches part of the left-hand side. So I'm going to keep that highlighted here to remind myself I'm keeping that locked. I don't want to touch that. Let me look at what the right-hand side is compared to the left-hand side now. Notice that both the left-hand side and the right-hand side, this blue highlighted stuff, they both have signs in them. So I'm going to go ahead and factor a sign out of those terms on the left-hand side just to work with that a little bit. So I'm going to, again, pause on this side. You don't have to write in these pauses. I'm just writing them in just to make my life a little bit easier. I'm going to unpause on the left-hand side, and I'm going to factor a sign out of this group. Sine of theta. I know I distributed that sine of theta in, but that helped me see something. But now I'm going to go ahead and just rewrite it back like this. Remember, I have plus this sine of theta, cosine of 2 theta. Remember that sine of theta, cosine of 2 theta, that's locked because it matches our other side. So I'm going to keep that locked. And notice now that both the left-hand side, the writing in green, and the right-hand side both have a factor of sine in common. So we're getting close. Now, I'm going to trade out. I'm going to pause on the left-hand side. Pause. I'm going to unpause on the right-hand side. And when I unpause here, I'm going to trade out that cosine squared, this guy right here, for a power reduction. Cosine squared is the same thing as 1 plus the cosine of 2 theta over 2. So I'm going to rewrite this as times 1 plus the cosine of 2 theta over 2. And remember, we still have this plus sine of theta, cosine of 2 theta. And I'll highlight that because we're going to keep that locked. And let's see. Now we're almost done because those 2's will cancel. You can easily see that. So I'm going to go ahead and just cancel the 2's here. And if you cancel the 2's, these 2's right here, you'll have a sine of theta times the quantity 1 plus cosine of 2 theta plus the sine of theta cosine of 2 theta. And if you take a look at the left-hand side, that's exactly what it is. So equals left-hand side QED. Now, I have to admit, I took a very long route to this. There are faster ways of doing this. Well, maybe not. But in any case, I wanted to demonstrate kind of how most students are going to kind of work their way through a problem like this. It is not an easy problem, but fairly typical. So I want you to practice problems like this and get used to the idea of working on a side, pausing, moving to the other side, wiggle, move back, wiggle, move back, wiggle. It's like you're trying to move a piece of furniture into the right spot. You wiggle one side, wiggle the other side until you get it wiggled perfectly, right? I use highlighting when I'm instructing just to showcase what items we want to keep locked into place. And that's what I end up doing actually when I prove things. I get to a point and go, oh, look, the right-hand side, it has a sine of theta times cosine of 2 theta. And so does the left-hand side. So let's go ahead and lock those in place. And then I just want that blue highlight to equal the other blue highlight, which I erased, but you get the idea. So this is a good, robust example.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.